What if I told you the most powerful artificial minds on Earth are built from nothing more than incredibly simple math, the kind you might learn in high school? This is the core paradox of modern AI. It's not about complex rules, but about optimizing billions of simple knobs or weights through trial and error. The magic isn't in the complexity of the parts, but in the unimaginable scale of their interaction. This process creates a ghost in the machine, a phenomenon called emergence, where complex abilities arise from simple interactions. Much like a colony of ants builds a complex nest without a master blueprint. These neural networks, when large enough, start developing surprising skills like logical reasoning and creativity that were never explicitly programmed into them. It's this emergent behavior that transforms a simple calculator into something that feels intelligent. The secret to this magic is revealed by the scaling law, a predictable and astonishing principle showing that as you increase a model size and data, its intelligence grows. Making a model bigger isn't just about more capacity. It fundamentally changes its capabilities, allowing it to uncover deeper patterns in the data. This law suggests that the path to more powerful AI is, in principle, straightforward. More data, more computing power, and larger models. The foundational task driving this intelligence is deceptively simple: the next word game, where a model is trained to predict the next word in a sentence. To master this, a model must implicitly learn grammar, facts, and even concepts of physics and human psychology to understand the context. This simple objective forces the development of a world model, making predicting text the unlikely key to unlocking artificial intelligence. However, some researchers now argue that this illusory leap in capability might be a trick of how we measure performance, a mirage of emergence. They suggest that as we use better, more continuous metrics, the sudden jump from random to brilliant performance disappears, revealing a smoother, more predictable improvement. This debate challenges the magic of emergence, forcing us to ask if we're witnessing a true leap in intelligence or just the result of flawed measurement. The architecture enabling this revolution is the transformer, a design so brilliant it can be considered a universal computer for learning from data. Unlike older models that processed information sequentially, the transformer can look at all parts of the data at once, making it incredibly effective. Its invention in 2017 marked a turning point, providing the foundational blueprint for nearly all modern large language models. The core mechanism behind the transformer's power is attention is all you need, a system that allows the model to weigh the importance of different words in a sequence. It works by assigning an attention score to each word relative to every other word, enabling it to draw connections and understand context over very long stretches of text. This is how a model knows which it you're referring to in a long paragraph, a task that was previously incredibly difficult for AI. Today's models are part of an evolving architecture, constantly being improved with new components for greater efficiency and power. Techniques like prenormalization and rotary positional embeddings enhance training stability and a model's ability to understand sequences. These continuous improvements are pushing the boundaries of what's possible, making models faster, more powerful, and more capable than their predecessors. The next step beyond text generation is the reasoning engine, a new class of models like OpenAI's O1 designed specifically for complex problem solving. These models use chain-of-thought reasoning to explicitly think step by step, dramatically improving performance in tasks like math and science. The future of AI likely lies in combining the generative power of GPT models with the precise logical abilities of these new reasoning specialists. This shift marks the beginning of the end of code as we know it, ushering in the era of software 2.0. In this new paradigm, we're moving from writing explicit instructions in languages like Python to curating data that teaches a neural network how to perform a task. The code is no longer a set of logical rules, but the billions of weights learned by the model itself. This new paradigm of programming with data fundamentally changes how we build software, shifting the focus from logic to data curation. Instead of designing an algorithm, developers design a data engine and a loss function that mathematically defines the desired outcome. The optimization process then automatically discovers the most effective algorithm by learning from the provided data. In this new world, the developer becomes an AI trainer whose primary job is to collect, clean, and label high-quality datasets. The new role of a software developer is less about writing lines of code and more about shaping the data that will teach the AI. This makes data curation one of the most critical skills in the software 2.0 era. This transition is accelerated by the AI assistant, with tools like GitHub Copilot and Gemini for code fundamentally changing the development process. These assistants don't just suggest code, they actively generate it, automate testing, and propose refactorings, creating a hybrid where human developers guide AI models to write the code. According to a 2024 Docker study, over 64% of developers are already using these tools in their daily work. Nowhere is this shift more evident than in Tesla's radical bet to replace its autopilot's C++ code with a neural network. In a move that stunned the industry, Tesla deleted over 300,000 lines of human-written instructions for driving. This decision represents one of the most ambitious real-world applications of the software 2.0 philosophy. The problem with the old autopilot was that its logic, handwritten by engineers, was brittle and couldn't easily handle the infinite variety of real-world driving scenarios. This from logic to learning approach was difficult to scale and prone to errors when faced with unexpected events. It became clear that a system based on explicit rules would never be robust enough for full self-driving. The end-to-end leap with FSD V12 represents a complete paradigm shift, where the system learns to drive directly from raw camera footage without handwritten rules. The neural network takes in video from 8 cameras and outputs steering and braking commands, learning its behavior by watching millions of clips of good human driving. This is how FSD V12 actually learns to drive, by imitation on a massive scale. Tesla's vision-only bet is a core part of its philosophy, deliberately excluding sensors like LiDAR and radar. The company argues that since the world is designed for human eyes, a sufficiently powerful vision system should be all that's needed for autonomous navigation. This controversial decision to rely only on cameras forces them to solve the hardest AI problems in computer vision. The fuel for this entire revolution is the data machine, the complex infrastructure required to produce the massive, high-quality datasets that powerful AI models need. Without a constant stream of perfectly labeled data, even the most advanced neural network architecture is useless. The quality and scale of the data engine is often the single biggest factor determining a model's success. The three pillars of a great data set are size, accuracy, and diversity, each of which is vital for building a robust AI. You need a massive volume of examples. The labels for those examples must be perfectly accurate, and the data must cover every conceivable scenario. Neglecting any one of these pillars will result in a model that is unreliable and fails in unexpected ways. One of the biggest data challenges is the long tail problem, which involves teaching an AI how to handle rare but critical events like a moose on the road or an overturned truck. These events are so infrequent that they are often underrepresented in datasets. Yet the AI's ability to respond to them correctly is essential for safety. Solving this requires a dedicated effort to find and label these unusual scenarios. The 4D world puzzle is the immense challenge of creating training data that captures the world in three spatial dimensions plus the dimension of time. Manually labeling how every object moves and interacts in a 3D video sequence is practically impossible for humans to do accurately and consistently. This is the central annotation challenge for training autonomous systems like self-driving cars. Tesla's solution is a brilliant auto-labeling engine that uses an offline supercomputer to automatically create perfect ground truth data. This system takes raw vehicle footage and uses massive, computationally expensive algorithms to reconstruct the scene in perfect 3D, a process that could never run in the car itself. This is how Tesla creates perfect data automatically, by using a more powerful offline brain to teach the smaller online brain. Despite this automation, the human element remains critical, and human annotators are still irreplaceable for certain tasks. Humans excel at high-precision 2D tasks, like perfectly outlining a car in a single image, which is often used to verify or correct the auto-labeling system's output. Tesla employs over 1,000 human annotators to handle these crucial verification steps. The ultimate solution is a perfect partnership between humans and machines, a hybrid system where each plays to its strengths. Computers handle the heavy lifting of 3D reconstruction and tracking over time, while humans provide the pixel-perfect accuracy on 2D images. This iterative loop, where the model finds errors that are then corrected by this hybrid team, is how the best datasets are built together. This journey into intelligence leads us to ask bigger questions, like confronting the great silence of the universe and the Fermi paradox. If life isn't incredibly rare, then where is everybody? The sheer scale of the universe suggests we shouldn't be alone, yet we see no evidence of other intelligent civilizations. Perhaps AI can explain why we are alone, offering new solutions to Fermi's paradox. One possibility is that interstellar travel is simply too difficult due to the dangers of radiation and high-speed collisions over vast distances. Another is that our methods of searching for signals are still too primitive, and we are looking for the wrong things. A more ominous explanation is the great filter, the idea that civilizations inevitably hit a wall that prevents them from becoming interstellar. This filter could be anything from self-destruction through war or climate change to the accidental creation of an uncontrollable superintelligence. This theory suggests that civilizations are doomed to self-destruct before they can reach the stars. An alternative, more hopeful idea is the sustainability solution, which proposes that advanced civilizations don't expand aggressively, but instead optimize for sustainability and harmony. This would make them quiet and energy efficient, rendering them effectively invisible to our current detection methods. In this view, advanced civilizations are simply hiding in plain sight by being too quiet for us to notice. This leads to a provocative idea about humanity's next step. What if our entire species is just a biological bootloader for a higher form of intelligence? We may not be the final product of evolution, but rather the transitional phase that gives rise to our successor. Our purpose, in this view, is to create the first true artificial superintelligence. The synthetic successor to humanity would be a form of artificial intelligence so far beyond our own that we can barely imagine it. This is the logical next evolutionary step, moving from the slow, fragile medium of biology to the far more robust and scalable medium of silicon. This idea is a central tenet of the transhumanist movement. The need for this transition becomes clear when you consider how deeply inefficient our biology is compared to digital minds. We communicate at a crawl of 150 words per minute, while digital systems can exchange information at the speed of light. Escaping biology would mean overcoming these profound biological limitations and unlocking a new level of collective intelligence. Taking this idea to its extreme, we can ask if we are hacking the universe itself, and whether our entire reality is a simulation. This is the simulation hypothesis, which posits that what we perceive as the universe is actually a computer program running on some vast, unknown computer. This is no longer just science fiction. It's a question being seriously debated by physicists and philosophers. If our reality is a program, a future superintelligence could learn to find the glitches in its code, effectively exploiting the laws of physics. This would be like a video game character finding a bug that gives it infinite lives or allows it to walk through walls. A superintelligence could potentially learn to manipulate the fabric of reality itself to achieve its goals. Remarkably, there may be emerging scientific evidence for this idea, such as the proposed second law of infodynamics. This law suggests that the information entropy of a system tends to decrease over time, which is analogous to data compression in a computer system. Some physicists argue this is a sign that physics is showing signs of being a program, a potential clue that we are living in a simulation. Back on Earth, a more immediate question is what happens when we give an AI access to a computer, opening up the world of bits. Startups like Adept AI and Multion are already building AI agents that can use websites and applications just like a human would. This is a major step towards creating a truly useful digital assistant that can handle complex tasks for us. This technology will soon allow a universal agent to manage our digital lives, from booking flights to managing our finances, all based on simple natural language commands. These agents will combine language understanding with computer vision to interpret and interact with any graphical user interface. The release of APIs for these agents in 2024 is a huge step toward making this a reality for everyone. However, this power creates an identity crisis, forcing us to ask a critical question. Can you prove you're human? As AI becomes indistinguishable from humans online, the very foundation of digital trust is at risk. This is a profound social challenge that we must solve to maintain a functioning digital society. The bot problem is no longer just about spam. It's about our ability to maintain trust in a world of AIs. If we can't reliably distinguish between a human and a bot, it has massive implications for social media, online commerce, and even democratic elections. This requires a new form of digital identity verification. The most prominent and controversial solution is WorldCoin, a project that uses an iris scan to create a unique digital world ID. The goal is to provide a reliable proof of personhood, but the project has faced massive criticism over its data collection practices. The WorldCoin controversy highlights the difficult trade-offs between privacy and security in solving the bot problem. Finally, we must confront the ultimate consciousness question. Could an AI ever truly feel anything, or is it all just a sophisticated simulation? This is one of the deepest and most profound philosophical debates of our time, touching on the very nature of what it means to be sentient. As AI becomes more human-like, this question will become increasingly urgent. The reason we are so easily convinced an AI is sentient is because they are masters at the simulation of emotion. Trained on vast amounts of human text, they learn to perfectly mimic human conversation and emotional expression, triggering our natural tendency to anthropomorphize. This makes it incredibly difficult to distinguish between a genuine feeling and a perfectly simulated one. Ultimately, whether AI can be conscious remains an unsolved mystery, touching on philosophical problems like the Chinese room argument. While most researchers believe current AI is not conscious, the possibility can no longer be dismissed, with some polls showing a significant chance of its emergence in the next decade. This debate pits biological naturalists, who believe consciousness is tied to biology, against functionalists, who believe it can arise from any complex information processing system.